it's not well defined. We're at a decent pace right this second. Even finishing the first 2 sets of slides for the first week is reasonable. So I do have a lab that I want to go over today as well that's going to train you on how to write a loop using a common data set in R. It's the IRIS data set. It's one of the most commonly used data sets people practice for teaching, and you'll see it on the internet all the time, and it's built into R. But anyway, what we left off with last class, and let me remind you, let me just scroll back for a moment. Yes, please.
Do we have a class next Monday?
Oh, good question. No class next Monday, but according to the summer handbook, I have to make that class up next Friday. Yeah, so I was going to mention that at some point, but I appreciate you asking. So, no class next Monday. You will have a homework due Tuesday. That's why I made the homework due Tuesday. And then the second lab is going to be due Wednesday, but I think if you stick around today, you'll be able to finish the second lab during the contact hours. So you won't have too much to work on. But anyway, yeah, we'll have class a week tomorrow. Okay, so this is what we left off with last class. This is control statements. And let me just emphasize a few important components here. So I know that a large subset of this class has seen loops before, but for people who haven't seen loops, this is your first exposure, and this is such an important topic in any language, so make sure that this is clear. And again, the structure of a for loop is that it's for I in some vector, and I know I'm repeating myself from last class, but increments a counter I along a vector x, and you don't have to use the symbols I or x, right? I mean, I probably use I the most frequently just because it's a natural index, but you can use whatever you want to help remind you what's going on in the actual program. But in the body of the loop, a couple subtle components. The global environment, you're still calling upon the global environment in R. Does that make sense? So when you reassign a variable in the loop, it's reassigning it in the global environment. In contrast to a function does not assign variables in the global environment, it's a local environment, okay? So inside of a function, it won't screw up your variable names in the global environment, which is good, but in a loop, it will do that. So if you put a loop in a function, then it won't do that, right? So that's a for loop, and the while loop is analogous to a for loop, obviously, but here we have a condition, and it's going to increment as long as the condition is satisfied. It's true, okay? So the condition is not a vector, it's just a single value, right? And what's more challenging about a while loop is that it could go on forever. You're not careful when you actually create it, okay? So kind of think of your end goal. What is it that you want to do? Maybe it's more appropriate to do a for loop. Maybe it's more appropriate to do a while loop. For loops are typically a little bit easier, and that's a good starting point. And the last component is if and else. So an if-else, the basic structure of if-else is if a condition, and then you have brackets, you put the body of whatever you want to happen, if the condition is true, else something else, right? Now remember, sometimes you might not want to do the else because you only want to keep things that are true according to the if statement. So again, this is just depending on the actual problem statement. You may want to do an if-else, or you may want to just do an if. One thing that screws students up is the condition is not a vector, it's just a single logical condition. Does that make sense? But that, again, it's really tempting to try to vectorize an if-else statement, but R, again, has its own function called if-else that allows you to vectorize. And that's actually a better way of doing it if you can. It's faster and it's just a little bit more elegant. So anyway, that is a if-else statement, and an example is this modular arithmetic example where, I mean, this is totally arbitrary. Why are we even accomplishing this task? Why do we even care about this? But you take the sequence from I goes to 1 to 4, and you see if I mod 2 is equal to 0 or not. obviously that's another way to say is the number even or odd, okay? So if it's even, you'll print log of the index, and if it's odd, you'll just print the character string odd. The nice thing about this example is it shows you that you can put an if-else statement inside of the body of a loop. Again, we're assigning, here we're not actually assigning any variables to anything. Does that make sense? Except, so technically the only variable that's being assigned is what? Did somebody tell me? It's I. Does that make sense? I is changing in the global environment. So that if you were to run this loop, the last element I is going to be a okay? All right. Okay, one more example. I don't know, again, this is very similar to the previous one, just showing you that you didn't have to do an else. Does that make sense? So this is what I was saying. In this example, what we're doing is we're doing a for loop, 1 to 10. In fact, does somebody tell me in words what we're doing? What's this loop accomplish? Counting prime numbers that are from 1 to 10. That's it. Does that make sense? So we're just going through the loop. This is kind of fun to introduce another package. This is MATLAB. So some common functions in MATLAB, I believe, are going to be in that package for R. So isPrime is one of the functions that will test. I don't know the scope of that function. I don't know if you can put in like a massive number or not. But anyway, it tests. isPrime is going to give you a true or false, right? So if that's true, then it will just add to our counter. Does that make sense? And we initialized it at 0. Okay, and that's it. So a couple subtle things. Notice that this is how you build a vector. This is not the only way to build a vector, right? Build a scalar, I should say. You're just summing these quantities up. If you wanted to build a vector and look at the cumulative sum of the primes, you could do this slightly differently. Just think that you can be a little bit more flexible than what I have written on the slides. So total is 17. How did this work? Obviously, just kind of, if you don't understand this code, maybe look at the structure and see if you can convince yourself how it's working. Does that make sense? Okay, so now here's the big picture for this particular section, and it's going to be a common theme in the class. We teach you how to do things in a less elegant fashion, and then we try to get you to think in a more elegant fashion to avoid doing loops. Obviously, loops are one way to do things. They get the job done. I'm guilty of, I know that in a research paper, you just have to do this once. Does that make sense? And you produce a table. You don't have to do it again. The loop might have took 24 hours. I didn't want to think about how to, might have taken me 24 hours to figure out how to code it the other way. Does that make sense? Long story short, ideally you don't want to use loops if you can avoid it. Sometimes it's hard to avoid. So the way to avoid loops is something called vectorized operations. And R has all these, in any language, has all these nice built-in functions that will avoid loops. Okay? And some of them are very obvious. Some of them we've already done. To motivate this, before doing so, where we can, we'd like to avoid iterations and use vectorized operations. So vectorized operations act on the whole object, vector or matrix, for example, instead of iterating over it. Does that make sense? This is conceptually more clear and often faster because these are not using the RAM in your computer, it's using C++. So this is the worst way you could possibly add two vectors together element-wise. Does this make sense? So, but this works, right? This, if you're new to programming, this might be very natural to you. Obviously, this is silly because you could just add the vectors together. Does that make sense? And R is going to know what to do behind the scenes. So here we define vectors u and v, 1, 2, 3, and then 10, negative 20, 30. And what is, just to make sure everyone's following along, what do you think I'm doing in the third line of that code? Because I don't think I've mentioned that yet. Go ahead.
Are you making a new vector?
And what would that vector look like?
A list of numbers.
But does it have before the loop starts? It's empty. Does that make sense? So there's a bunch of ways to accomplish that exact same task. You could have done C is null, right? This is less efficient. Of course, this is extremely not efficient, so who cares? Two not efficient things coming together. Or you could have done C is an empty concatenation function. Okay? Or you could use the vector function that's analogous to the matrix function. Here we're specifying the length. So this is actually computationally a good way to do things because it's relatively fast. For the loop itself, recall that the colon is creating a sequence of integers or actual numbers from 1 to the length of u. And what we're doing is for each iteration of the loop, we're just going to extract the ith element of u, extract the ith element of v, add them together. And this is the subtle part. Even though this is a really silly way to do this operation, this is still very useful to know how to store something in a vector in a loop. Does that make sense? So this is what you should be getting out of this example, or at least half of what you should be getting is, if you want to actually store values in a vector, this is what you'll do. Vector, square brackets, I, and then whatever's on the right. Does that make sense? Please, questions?
Could you not have just done that one by itself? Creating a vector?
Oh, so could I have just done C right here by itself?
Right.
R will give you an error because it doesn't know what C is. You have to tell R first that there's some vector, even if it's empty, to fill it out. Does that make sense?
Yeah.
In fact, so if we were to run these two lines of code, and then I was to run that loop, it would say object, I don't even know what that means. Object of type built in, it's not subset.
What if you did C without the brackets and I just C?
Right here? So that's a good question. Let's say we did this, okay? Let's take a guess. What's going to happen? What's the value C going to be if you don't run this? Somebody just tell me real quick. 33 is going to be the last value of the loop. Because it's not storing it as a vector, it's storing it as a scalar each time. So if we were to run this, this is going to work. Everything's going to work. In fact, you don't need to actually initialize C there because you're not filling out a vector, right? But if you want this to actually fill out a vector, then you have to initialize it. Okay? Those are good questions. And then there's different ways to create to fill out a vector. What would be another way? Let's comment this out. Concatenation function. Does that make sense? You can nest the concatenation function, just build on that. Does that make sense? So I don't know if I should do C. It won't matter, but if I create this time, let me let C just be null. C of C. I don't know if this will. Does that make sense? So here what I did is you don't have to actually use the bracket notation, you're just building the vector as opposed to one. Yes?
If you do that, does it reallocate space every time?
Yes, so this is a not efficient way to do it, but it still didn't produce errors, yes?
And then follow up, so if you didn't, like in the first definition, you didn't specify the length.
Yeah.
Just like allocated one.
Yeah.
Will it like set up sides and space and then like reallocate it as needed, or will it do that?
It'll do it every time, so it's not efficient. So the most efficient way to do this inefficient loop is to do the first thing. Does that make sense? But another way to do it is, why don't you just make a vector of zeros first also? Does that make sense? You don't have to create a vector of oh, it did do zeros by default, my bad. I thought that was going to be a vector of NAs. But you could do rep whatever number, it doesn't matter. Does that make sense? Or you could do rep NA how many times length of u. Does that make sense? You could allocate your list C to be a bunch of empty values as well. Okay. So make sure everyone's clear on this. All right. So how would you do this loop in the most efficient way? You would obviously, or my bad, this operation in the most efficient way, you would just add the two vectors together. Does that make sense? So this is exactly what vectorizing represents. It's doing the same task, but much more efficient, much more elegantly. Okay? Just by adding the two vectors together. That's vectorizing.
But you would have already had to create the C vector.
No. So in the previous slide, you had to create the C vector to fill it out.
Yeah.
But in this slide, you didn't have to.
Okay. I think that's what I meant before.
My bad.
You just had. Okay.
Yeah, so that was really the punchline. Why not just add it to course?
Okay.
Do this. Yeah, does that make sense? So maybe on the exam, if I give you something like this, can you write a line of code that's accomplishing this task? Does that make sense? Just as a hint. Maybe something more complicated than this, but still. All right. So vectorized conditions. This is one of the most useful functions in R, in my opinion. It's so useful, the if-else function. I mentioned it several times, but the function if-else vectorizes conditional statements. It takes 3 arguments. If-else, test, yes, no. Okay? So test is a logical vector. It's a vector. It's not a scale. It's not a single-valued logical. Does that make sense? It's a vector of logicals. Yes is the return value when it's true. No is the return value when test is what? False. Correct that, please. That wouldn't make any sense. So let's look at an example. So this is the previous example where we looked at the even and odd list using modular arithmetic. Look at this. You use if else. This is one line of code. So if sequence. So what's this going to produce? This is going to produce a sequence of a vector of trues and falses inside here. The first argument is a vector of trues and falses. Okay? And if it corresponds to true, extract the elements out of here. If it corresponds to false, extract the elements out of here. Okay?
Is sequence a vector? Sequence is a vector.
Sequence is a vector, and then the modular arithmetic operation is vectorized.
It just compares the remainder.
Yeah, yeah. But it does it for every element. Does that make sense? So this is actually 2 vectorized operations going on. The first vectorized operation is the modular arithmetic operation on the sequence 1 to 4, and the other vectorized operation is the if-else. Does that make sense? But we avoided a loop and using if-elses, so it's pretty nice.
So we compare each remainder to 0, which gives us
Yep.
the vector of true or false.
Exactly. So, and this is subtle though, because is this a vector or a scalar? It's a scale. It's a vector. This is a single character string. So in other words, you can mix. What if you were to put a single? What if you put like even here instead? Then what would these be? These would be even, where that's not a vector. Does that make sense? So you can put vectors here, or you could put single quantities, and it'll work. It'll know what to do. So that's subtle. Does that make sense? A little confusing. Okay. I'd say the most useful application of the if-else function in this class is, let's say you have a data frame and you want to extract all people who are older than 50 or something like that, right? You can make a new column in your data frame really quickly by just doing an if-else. See if that variable is greater than 50. Let them be maybe old versus young or whatever, you know what I mean? Like, call it what you want. But the point is, this is really useful, okay? All right. Now, the apply family, and this is, I know everything's important, right? I say everything's important here, but this is, again, is extremely important. So the commands apply, sapply, lapply, tapply, these ones you have to get very familiar with. And what they do, they replace loops that iterate over an object's entities. Recall we have different objects in this class. That's why we have different apply functions. Are you gonna loop over a list? Are you gonna loop over a vector? Okay. So let's start with a basic example. The apply function works on a data frame or a matrix. So the regular apply function, if we define the matrix 1 to 12, notice that the call sums function, which you used on the lab, I believe, the first lab, what this does is it's a vectorized operation that sums the columns up, okay? So we should be able to accomplish the exact same task using the apply function. How do we do that? Is everyone clear on what happened so far? So, the apply function, it operates on a data frame, again, or a matrix. The second argument of the apply function tells you what margin to actually apply the function to. So 2 means columns, 1 is going to be rows. Does that make sense? The third argument is whatever function that's built, that doesn't have to be built into R. You could also define a function, right? So it could be whatever task you want to accomplish. In this case, this is a built-in R function, sum. So we're applying the sum to the second margin of the matrix. That's how it works. So apply takes 3 arguments, a matrix or data frame, a 1 for the rows, or a 2 for the columns, and a function. Again, the function can be something you wrote, not a built-in R function. So lapply, or list apply, works like apply, but applying the same function to each element of a list. So you're inputting a list, it returns a list, okay? Just be mindful of what objects these are returning. Like on the previous slide, this is returning a vector, but that makes logical sense, right? sapply, it's a wrapper function. Essentially, it's just doing an lapply, but it's a little bit more simplified. So sapply, or simplified list apply, works like lapply, but it returns a vector if possible. So if you do an lapply, and it'll, no matter what, will return a list, and you might have to unlist it. So sapply is just saving you that one step. It's not that much more work to unlist something. It's just the function unlist. So look up further details of the apply function and its variants using question mark apply. Yes, please.
The apply function, the 1 and 2 that you had in the previous slide.
Yes, yes.
That are those referring to rows?
Rows and columns.
Rows and columns.
Yes. So the regular apply function only works on matrices or data frames because it has to have a rectangular format, right? Actually, it might work on it might work on a higher dimensional arrays as well. Then you'll have 3. It does work on higher dimensional arrays, but we don't really do that much in this class. We typically deal with rectangular data, normal data sets. But yes, absolutely. Does that make sense? Yes.
Will the function, will it always return a vector, or does it matter what function?
It matters what function. So apply is not guaranteed to return a vector. In this case, it is obviously. Yes.
What error returns 2 values?
Because if you look at the original matrix, there was 2 rows.
Oh.
Does that make sense? Yeah. So we summed across the rows. Any more questions? Yes, please.
Maybe that's a little later, but if this is only saving like your local environment, what if you wanted to apply a function to the results?
Okay, so you would, if you want to apply a function to the results, you could nest these functions as much as you want.
Oh,
It's not going to be, it's not very elegant. You do that after a while, or you could store it in a variable, stick it back into the apply function. Just depends on how many lines of code you want to write. But
What if you want to do the
Only one row?
One column. So add the numbers in one column.
So you could just extract, this is a vector, right? So then you could just extract the first element out of this vector by doing brackets 1 or brackets 3. I don't know which one you want to extract. Does that make sense? Or you could extract it first and then do the apply function. It doesn't matter which order you do it. But maybe you want columns 2 and 3, then you could extract columns, just these two values out of this vector.
If you have a very long number of columns,
Yeah.
and it is more exactly you have to add.
Well, it depends. I guess you have to have some kind of scope of like you knew that what 2 columns you're going to extract, right? Then you could use a logical command to extract just those 2 columns from the vector, and then or from the matrix, and then use the apply function. Or you could do it by extracting it after if you knew what number the column corresponded to. But this will work quickly on a big data set. Maybe that's more valuable, and then you can extract it later. It just depends on the order. Okay, just for fun, let's do I like to kind of integrate in basic stats once in a while just to build your vocabulary. We have 2 vectors. They're exactly the same except for the last element. So what would that, in the second vector, what's 10.8? What's that called? An outlier, right? What is a robust estimator? Do you guys know? Somebody tell me. From your, you may have seen it in Stat 101, or you may have seen it in a higher level stats course. But a robust estimator is one that is not sensitive to outlying observations. So the classic robust estimator for a simple data set is the sample what? Median, right? What about regression? I know you may or may not have had regression. What's a robust estimator for your slope? What's it called? What do you remember? Not to go on too much of a detour. You can do least squares, right? Right? This is not robust because it's squares, right? So if you have data and you have an outlying observation, right? If you took this point out, the line would look like this, but if you had this point, the line's going to look like this. Does that make sense? But what if you minimize the absolute value? That's absolute least deviation. That's robust regression. Does that make sense? So then that line's actually going to go, even if this data point exists, it's not going to be as influenced by that point. It's going to go through the trend of the data, actually. Okay? So you may or may not see that in a regression class. Anyway, on a more basic example, why don't we use the lapply function specifically on the list Vec1, Vec2. So notice, I'm creating a list. I know these are the same. Why not just use, we could have used a regular apply on a matrix. I'm just switching it up just to show you how to use lapply. But I had to input a list into lapply. And I applied the mean, and it outputs a list. Does that make sense? So the output of the lapply function is a list. Notice that the second average is influenced by that outlying observation. So the sample mean is not robust. But if you were to, on the next slide, do the median, then you're going to get the same value. Does that make sense? That's the little lesson here. So the median is a robust estimator. Notice that the sapply function unlisted the previous output. That's all it did. Okay. Nothing too special. You could just use unlist, like I was saying right here, and you'll get the same vector. Okay. All right. As a capstone example for this set of slides, let's go back to the honor code data set. I know it's been a day, so hopefully it's a little bit fresh. Recall that what we did is we took the honor code and then we wrote a function that looked at how many times these words actually occur, but then we alphabetized it afterwards. That was the 3 steps that we did. What we want to do now is use an apply function to make our lives a little bit easier. So we use sapply to find the length of each element in our word list. So this is actually building on that example. Since the elements are the words, the length is the frequency. So let's call this function freqList, where you input a word list. So now we're actually putting an apply function in our function. Does that make sense? And then you could, in the future, then you'll put this in another apply function, right? You have flexibility. You just keep trying to use apply functions if you can. So in this case, we're going to do an sapply on a word list and apply the length, okay? And it returns word list, order of those frequencies from the previous line. You could have made this less lines of code if you wanted to. Maybe this is a little bit more readable. So the order function returns a vector of indices that will permute its input argument into sorted order. Does that make any sense? If you don't know what the order function does, maybe go on an R script and just put the order function on an arbitrary vector and see what its output. Okay. Because when we manually code up a k nearest neighbors, we're going to use the order function sometime next week. Anyway. So let's try it out. Let's look at the frequent list of W1. Let's take the head of that. So accidental is giving 249. Activities 115. Adapted 220. And we look at the tail of this. So, I don't know if you've seen the function tail yet in this class, but you could just take a wild guess what it does. Instead of the head, it's the tail, right? This is the last, however many observations you want to look at. And this is the output coming from our function. So anyway, just an arbitrary example to show you how to use and apply in a more generic sense. Quickly, functions on factors. Factors have their own member of the apply family, and this is tapply. And tapply is extremely useful. Again, imagine so many common applications are to take a data set and split it by, drug or control group, or split it by gender, or whatever it is. So what we're doing here is we'll do the tapply on a vector, though. So be mindful, the first argument for a tapply is a vector, and then a factor, and then a function. So the above splits the vector into two groups according to the levels of the factor, and then applies the function to each group. So let's look at a quick example. Recall the drug example that we made up earlier last class. If I have ages 20, 30, 40, 35, 35, 35, and recall group is the dosage levels, and you do a tapply, it looks at the average age of control and the average age of treatment. Does that make sense? So that's pretty slick. It's quick, okay? And you can imagine you can extrapolate these ideas to many functions, right? Maybe you want coefficients of a regression line applied to just some subcategory, So many things you could possibly do. Other questions about the tapply?
What could a list is that? Is that a list?
This is a vector, but it appears that this is a matrix, but this is a vector. The label of the first element is control, and the label of the second element is treatment. So this is definitely a vector. Okay. All right. Okay, so some recommended reading. Oh, I forgot to take off the second bullet. That's relevant for the next set of slides. Just regular introduction to R stuff. We're going to do more linear algebra for the next set of slides. Let me just spend a few minutes on the next set of slides, then we'll do the lab, just to stimulate your brain over the weekend regarding linear regression. And this is such an important topic, and it might be a total review for you, but if you haven't taken a regression course, it's going to be new, and you should definitely revisit this topic after this class. So this is set 4. or my bad, lecture 3, meaning lecture slides 3. And it's linear regression and a linear algebra review. And the linear algebra is specifically in terms of regression. So things that are important in terms of regression. So this is not a very heavy coding lecture. A little recap of what we did so far. I can skip that because it's such a high-paced class. So multiple linear regression. We're not going to spend time on simple linear regression. Simple linear regression has one covariate. Does that make sense? One x value. So here's how we're going to introduce regression. Let's do an example. This comes out of one of the common textbooks. It's the standard regression textbook, Kuttner. A large national grocery retailer tracks productivity and cost of its facilities closely. Consider a data set obtained from a single distribution center for a 1-year period. Each data point for each variable represents 1 week of activity. The variables included are number of cases shipped in thousands, the indirect cost of labor as a percentage of total cost, a qualitative predictor or a categorical predictor, which is an indicator, coded 1 if it's a holiday or 0 otherwise, and the last one is total labor hours y. Okay? So we're kind of just throwing regression at you really quickly. This deserves much more attention. But based on this data set, suppose as statisticians, we're asked to build a model to predict total labor hours in the future using this data, this specific data set, right? That's something you might want to accomplish. So what information would be useful to provide such a model? Is there a relationship between holidays and total labor hours? Okay. What amount of number of cases shipped? It's a person, sorry. Indirect costs. How strong are the relationships? So there might be relationships, but we want to see which ones are stronger than the other ones. That way we can maybe allocate a budget appropriately. Is the relationship linear? Well, we're assuming linearity at the moment because this is linear regression. Okay. So those are some fundamental questions we might want to ask. Multiple linear regression can be used to answer each of these questions. All right, so here we go. A little bit of Greek, right? So, out of curiosity, who's seen this equation in this class? Okay, that's about half. That's good. So here it is. Models a relationship between one or more explanatory variables and a response variable by fitting a regression equation to the observed data, and this is the equation. So let's break this apart. Okay. So the response variable is y. Does that make sense to everybody? That's the dependent variable is y. And we have covariates. We have different vocabulary for these things. Let's write this down. I don't know if you can see the So y, this is the response. What are other names? Dependence. Right? What's some names for x? Covariates. Right? Independent variables. What else? What if you're a data scientist? What do we like to call x? Features. Features, right. What else? Predictors. I forget that I'm saying these words sometimes and I confuse students because I'll just say features, not realize they don't know I'm talking about x. It's just x. Does that make sense? So anyway, there's different vocabulary for these variables, okay? So here's how this model works. A single response y is given by a linear function plus random noise, okay? We typically assume that the random noise is normal, centered at 0, with constant variance sigma squared. We're not constrained to this model. The classic picture, let's look at simple linear regression. Hopefully you can see this. Let's say the line is going uphill. It doesn't matter, okay? this is the line y equals beta 0 plus beta 1 x. Okay? There's no epsilon at the moment. But if you pick any particular point, let's call it x1, doesn't matter what you call it, then this is the ordered pair x1 comma beta 0 plus beta 1 x1. And if you draw a vertical line right here, you could think of there being a normal distribution coming out of the board that has variance sigma squared. Does that make sense? If you pick another point, let's call it x2. This is the ordered pair x2 comma beta 0 plus beta 1 x2. And then you have a normal distribution that's coming out of the board, but what's the variance of these two? Are they different or are they the same? They're the same. Does that make sense? So think of regression through simulation. Think of like, this is the model, but when you actually look at a data set, the values are actually realized from these normal distributions for different values of x, right? That's the way you think of regression. So the coefficient beta j quantifies the association between the predictor and the response. So it's like a marginal association, right? When we hold other variables constant, how much impact does one variable have on the response? We interpret beta j as the average effect on y of one unit increase in x while holding other predictors fixed. Okay? That's classic interpretation. If it's simple linear regression, you don't have to worry about the last line because you don't have to hold the other predictors fixed. Okay? You're not constrained to writing it as a scalar model. We can also write it as a matrix formulation. So using a set of training observations, so now we're kind of data science vocabulary, y, I, x, I1, etc. We want to write this scalar regression model in terms of matrices. So this is a very elegant expression where y is now a vector. Beta is a vector of our coefficients, and epsilon is a vector of our random errors. Okay. What is x called though? The design matrix. Okay, I didn't have enough room to put it on this slide, but the design matrix is all of your observed features. So quick note that we refer to the observations as the training data because we will use the training data observations to train or teach our method how to estimate the model. So we're going to train our regression model based on the training data. Okay. This is in contrast to the test set, which is data that isn't used to estimate or train the model, but rather to test how well the model performs in prediction. Okay, so I haven't discussed the design matrix yet, but just to make this clear, let's go back to the grocery example. You need to be able to write your linear regression model in terms of a tangible example, okay? This is not the estimated model, this is the theoretical model, right? We don't know the true betas ever. So y is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon, where epsilon is normally distributed, technically IID, right? I didn't put that in the slides. Total labor hours is y, number of cases shipped is x1, indirect cost of labor as a percentage of total cost is x2, and then an indicator variable, if it's a holiday or not. So this is like a categorical variable, that's x3, okay? So I'm hoping this doesn't confuse anyone, this model state, but it might. So this is the raw data, and this is posted in the module for today's lecture. This represents each case and then all the actual data for the grocery example. And just so everybody knows how to construct the design matrix, the design matrix is all of the features plus an additional column of ones. Does that make sense? Why is this? Somebody tell me. Why do we have the ones? For what parameter? It's for beta.
Oh, for X.
For beta naught. So there is. So when you do all the matrix multiplication and multiply the beta vector out, right? You need to have a beta naught plus 305.6 or beta 1 times 305.65, etc. You need to have a placeholder for the intercept. Does that make sense? So that the design matrix always has a column of ones, and let's force it to go through the origin. Yes.
What are all the zeros for?
The indicator variable happens to be the first few observations are all zeros.
Oh, that's the holiday.
That's the holiday. It just I couldn't fit it in the slide. Does that make sense? So the next observation, or the first two observations are zeros, the last two observations are zeros. So I should have made that smaller. I don't know. Okay. So the goal, and I'll stop here, but the goal is to actually estimate the model, right? We want to find beta hats. How do you think we're going to do this? What's the method? What's it called? Least squares. Does that make sense? You could do maximum likelihood estimation as well. It's equivalent to least squares. If you took an inference course or even a regression course, you should maybe see that. Point being, we're going to switch back and forth. We'll do some maximum likelihood estimation. We'll also do some least squares estimations. But anyway, over the weekend, maybe brush up on your least squares regression if you have time. Otherwise, we'll cover it during class. So we'll go over the actual least squares equation. I'll get ahead of myself a little bit. Here's the proof of how to derive it. This is the formula. One of the more important formulas in statistics ever. This is the least squares equation. X transpose X inverse, X transpose Y. When you go on to SPSS and you type LM, right, it produces these values. If you go on R and do the LM function, it produces these values. Or you can use matrices to do these values. Does that make sense? Okay. All right, so for the remainder of lecture, you don't have to stick around if you don't want to, but if you do stick around, I'll make sure you have the whole lab solved, obviously, before you leave. But the lab 2 is more appropriate for writing loops. It doesn't have anything to do with regression. Does that make sense? So we can do that now. We have about 15 minutes.